Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon. But ever find yourself lost in the ticking hands of time, wondering if our understanding of it is just the tip of the temporal iceberg? At its head, his revelation is not just a theory. It's a key that could unlock the doors to the mysteries of the cosmos, revealing a universe more intricate and inspiring than we ever dared to imagine. How does Brian Cox's new theory challenge our traditional understanding of time? And what are the potential implications for our perception of reality? Join us on an intriguing exploration through the annals of time itself as we delve into Brian Cox's recently revealed groundbreaking theory on the nature of time in the vast universe around us. Mysteries are waiting to be uncovered, and some of these mysteries involve puzzling things about time and gravity, which are essential parts of our existence. Imagine a world where time acts strangely. It can either slow down or speed up. Also, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a peculiar turn. Albert Einstein, a well-known name, provided us with a new way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves in different situations, especially when traveling at extremely high speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the idea of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a diagonal path. Now, here's the interesting part. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So, in this scenario, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, is not just a theoretical idea. Scientists use big machines called particle accelerators like the Large Hadron Collider to make particles go super fast, almost as fast as light. When things move this fast, we have to think about time in a special way to make accurate predictions and measurements. Albert Einstein came up with the special theory of relativity in 1905, and it changed how we see the universe, especially when it comes to time and movement. This theory challenges what we might naturally think. It says that the rules of physics are the same for everyone, even if they're not moving. This is different from our everyday experience, where we might think that if something is already moving and we add more speed, it gets faster. But Einstein's theory says there's a maximum speed that nothing can go faster than, and that's the speed of light. In this way of thinking, events that seem to happen at the same time for us might not seem that way for people moving around almost as fast as light. Another thing that comes from this special way of looking at things is length contraction. This means that if something is moving, it looks shorter in the direction it's moving when you look at it from a spot that's not moving. And then there's this famous equation: energy equals mass times the speed of light squared. This equation comes right out of this special way of thinking. It shows that energy and mass can change into each other, which is a big deal for understanding how tiny particles act when they're zooming around really fast, and also for things like what happens when atoms split in nuclear reactions. In the real world, special relativity isn't just a fancy theory, it's something we use in everyday technologies like GPS. When GPS satellites send signals to your device, they're moving, and because of this motion, time behaves a bit differently for them. If we didn't consider this time dilation effect in our GPS calculations, your navigation would be way off. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This idea challenges what we usually think about time and space. It's like saying our normal understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Some fundamental ideas, like the speed of light always staying the same and how energy and mass are connected, have been proven by lots of experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory goes deep into the relationship between gravity and how the universe is put together. It shakes up the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because space and time are curved or bent. It's like saying, hey, gravity isn't a mysterious force. It's just how things naturally move in the universe. According to Brian, understanding general relativity means thinking about the universe as a four-dimensional thing, combining 3 dimensions of space and 1 of time. In this framework, big things like stars, planets, and even us affect how space and time are shaped around them. This shaping is what we see as gravity. Imagine space-time like a big stretchy blanket. When something heavy like Earth is put on it, it creates a dent in the blanket. If you put something smaller, like a ball, near Earth, it will roll toward this dent. This is similar to how objects act because of gravity, not some mysterious force, but a reaction to the bending of space-time. General relativity provides a solid explanation for how things move in our solar system, like the planets going around the sun. It can accurately tell us the paths these planets take, including how Earth follows an oval-shaped orbit around the sun. According to Brian, this is different from the old idea of gravity just pulling things together, which had a hard time explaining how planets move like they do. The new idea is that space and time are curved like a bendy fabric, and that fits better with what we see. A big moment that showed general relativity was right happened during a solar eclipse in 1919. Sir Arthur Eddington led a team to watch how light from faraway stars bent as it passed close to the sun. According to the theory, the sun's big mass would make the starlight curve a bit. During the eclipse, the observations precisely matched Einstein's predictions, establishing the validity of the theory. Just like motion can change how we experience time, according to special relativity, gravity also has an impact on time. In places where gravity is really strong, time moves more slowly compared to areas with weaker gravity. So, if you were standing close to a huge object like a black hole, your clock would tick more slowly than one placed far away from this powerful mass. General relativity introduces the idea of black holes, spots where gravity is super intense. Inside a black hole, the gravitational force is so powerful that nothing, not even light, can escape from it. The edge around a black hole is called the event horizon, and it's like a point of no return. Once something crosses this boundary, it gets pulled into the black hole without any chance of coming back. Einstein's theory of general relativity has big implications for how the universe is structured. At first, he added something called a cosmological constant to his equations because he thought the universe was not changing. But when we found out it's expanding, he called this a big mistake. This idea of an expanding universe based on general relativity is a key part of the Big Bang theory, which explains how the universe began. Another important idea from general relativity is about gravitational waves. These are like ripples in the fabric of space and time caused by really heavy things moving fast, like when black holes or neutron stars come together. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, proving another part of Einstein's theory. Over time, scientists have conducted numerous tests to check if general relativity is true, and each time it has proven to be right. Whether observing how planets move, the bending of starlight, or the detection of gravitational waves, the theory has consistently been supported by evidence. While saying gravity is a lie might be surprising, especially since we all experience gravity every day, in the world of physics, it's normal to discuss and explore different ideas. Scientists like Brian often question established theories, and with gravity, some people challenge the usual way we think about this basic force. One idea challenging traditional gravity is called modified Newtonian dynamics, MOND. MOND suggests that gravity acts differently at slow speeds, especially in galaxies, without needing dark matter. Instead of adding invisible matter, MOND proposes that gravity gets stronger at low speeds. The gravity debate also involves mysterious dark matter and dark energy. introduced to explain certain phenomena in space. Critics argue that these are not needed, and alternative ideas can explain what we observe. Some scientists who disagree with Einstein's gravity theory explore new possibilities, such as theories involving unknown particles or forces that could change or add to our understanding of gravity. It's important to stress that in science, new ideas are not ignored. Instead, they are carefully tested to see if they make sense. For example, Einstein's idea about time in four-dimensional space, where going back in time might be limited by the speed of light, has been creatively considered alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that going back in time seems unlikely from a physics viewpoint. Ongoing experiments and observations check if these new theories can explain things like the force of gravity in a similar way to what we already know. While various ideas have been discussed, none have convincingly replaced the well-known rules of gravity. Doubting and disagreeing with ideas are crucial parts of how science learns new things, leading to more research and a better understanding of the universe. In the world of gravity theories, general relativity remains the most important and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as how planets move and how light bends around massive objects. General relativity remains strong because it's simple and covers a wide range of phenomena. As we discussed before, Einstein's special theory of relativity suggests that time can act differently based on how you're moving. Now, let's explore how this idea affects real-life things, especially in space travel. Space travel is exciting but challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go in space. This makes traveling between stars a significant challenge, even with super-advanced technology, due to the long time it takes to reach the closest stars. Consider the famous twin paradox to understand what happens with time when you travel in space. Picture this: one twin stays on Earth, and the other twin goes on a trip to a faraway star. When the space-traveling twin comes back, they find out that less time has passed for them than for their twin on Earth. This means they kind of travel into the future. Time is crucial for space travelers because the longer the journey, the more time slows down. If astronauts go to nearby stars where time slows down a lot, they might age more slowly than people on Earth. While it might sound like a sci-fi story, it's a real effect from the theory of relativity. Imagine if humans sent a crew to a star system not too far away. Because it's such a huge distance, the trip could take many years. Even if they go fast, for the astronauts on the spaceship, time would feel shorter because of this time slowdown. But on Earth, a lot of time would have passed. Time dilation not only affects living things but also impacts technology. Computers and communication devices on spacecraft need to consider time dilation for accuracy and proper functioning. Space travel challenges at high speeds involve physical aspects like extended isolation and exposure to cosmic radiation, as well as the psychological effects of being away from Earth for a long time. In our daily lives, we can see the effects of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's crucial to factor in these effects for accurate GPS calculations. Failing to do so would significantly affect the precision of navigation systems. Now, let's explore why time moves in one direction. Time governs our lives in the universe, flowing from the past to the present and into the future. This one-way journey of time is fundamental to our existence. But why does time have this one-way nature? To understand, we look at entropy, a concept measuring disorder or randomness in a system. Entropy, linked to the arrow of time, tends to increase over time, causing time to flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or at best remain constant. In simple terms, entropy naturally tends to grow and doesn't decrease on its own. Watching how things get more disordered around us helps us see the one-way flow of time. Imagine a deck of cards all neatly arranged. If we shuffle them, they become messy and random. This change from order to disorder shows how time moves in one direction, as seen in everyday phenomena like ice melting or a stirred cup of coffee becoming messy. This flow of time works differently at different levels. If we look closely at tiny particles, the rules of physics allow things to go backward and forward in time, a concept known as time reversal symmetry. The contradiction between this and the irreversible changes we see in the everyday world comes from something called initial conditions. The big, complex world we live in is the result of many particles and how they interact, creating a one-way arrow of time. This idea of time moving in one direction isn't just about everyday stuff. It's also true on a cosmic scale. The whole universe has been evolving in one direction since the Big Bang. The universe started in a low-entropy state and, over billions of years, has become more disorderly, forming galaxies and stars. Scientists are still figuring out why the universe began in such an ordered state. Even in the tiny world of quantum mechanics, which deals with really small particles, there's a time arrow. The way particles change over time seems to be symmetrical, but when we observe them, things become irreversible. Brian believes that it's not just a physics thing. Our brains also experience time in one direction. We remember the past, live in the present, and think about the future in a sequence. This mental arrow of time is connected to how we see the external world's arrow of time. This concept of time has deep philosophical implications, challenging how we understand reality. Reality is a fundamental part of how we experience life and understand the world around us. Without this one-way flow of time, everything would be very different, with no consequences for our actions, and cause and effect wouldn't make sense. Do you believe that time dilation, as explained by Einstein's theory of relativity, could make time travel into the future a reality for space travelers?